Hello everyone. In the previous lecture, we were discussing uh, the complementary energy, and that concept of the complementary energy will pave the way for something extremely important in our discussions of energy methods called the Castiglione's theorem. And it is this Castiglione's theorem whose application will enable us to solve a number of very useful engineering problems. Now, as a first step towards that useful theorem, we are first going to discuss this rather long-looking name of a theorem, generalization of Castiglione's theorem of least work. Now, because of whatever historical reasons, it has been named as such, but the but the real point here is that this theorem that we are going to discuss, uh, uh, it doesn't really directly involve any work, nor does it deal with anything least or minimum. Rather, what it actually deals with is uh, an extremization of something which is referred to as the modified form of the complementary energy. Okay, so we had discussed about the complementary energy in the previous lecture. Today we are going to discuss the modified form of the complementary energy. We are going to define that, and then you'll see that this theorem, it will deal with a certain version or certain use of that modified complementary energy. So what is this theorem all about? Okay, so I'm not going to write the grand formal statement of this theorem. That is very much present in our lecture notes. You can refer to that later on. Let's discuss this again in a very utilitarian fashion. Okay, so consider, as always we do, a general three-dimensional body. Okay, something like this. Maybe I use a different color for this. We consider a general three-dimensional body like this, and you consider various uh, you consider uh, a very general way uh, of the boundary conditions which is set here. So over a part of this surface of this body, so if the entire surface is denoted by S, let us say that over a part of the surface may be from here to here. Okay, maybe I use a different color also for that. uh, Maybe from here to here, all over this, that is given by S1 part of the surface, and over here the traction is specified. Okay, and over the rest of it, we use a different color for that. Over the rest of it, let's say that it is S2, it is the displacements which are specified. Okay, so over this S1 part of the boundary, tractions are specified, and over the rest of it we have displacements specified. Now, what this theorem, okay, you may call this, if you want, the modified complementary energy theorem, if you like. So what this theorem is stating is that of all the stress states that may be possible in response to this kind of attraction and displacement boundary conditions, the actual state of stress that will be present in this body, that will correspond to uh, an extremum of something called the modified complementary energy. Okay, so I repeat, of all the stress states that are possible, which satisfy the mechanical equilibrium equations and the boundary conditions, everything. Okay, so the actual state of stress that will be possible over the body, that will correspond, that real answer will correspond to an extremum. Okay, mind you, it is not the minimum or the maximum, it is the extremum of the modified complementary energy. So in very short, what this theorem is basically telling us is that the stress state will just correspond to this, where this capital psi, the first variation of this capital psi, this capital psi, uh, this capital psi, it corresponds, it is the modified complementary energy, and I'll define this in just a moment. So it is defined uh, as u dash, which, as we have mentioned in the previous lecture, this u dash is the complementary energy minus integration of ui ti ds. So this is a surface integral, but very importantly, please note that this is the surface integral over just the S2. Okay, it is not over the entire surface of the body, but it is over S2, and we'll see how it comes about. Okay, so this is a theorem. We will formally say that we are going to go about with a proof of this theorem, but uh, uh, but before we can actually launch into the proof, there are a couple of things which you should note. Okay, so before going into the proof, uh, a couple of things to note. Okay, so the first thing to note uh, is that because the body will be in equilibrium, we know for a fact that our stress equilibrium equations will hold true. So we have this thing. Now, uh, we take the first variation of this and see what that gives us. Okay, so if we take the first variation of this, we'll put the variation symbol here, and then we can take that inside the partial derivative to obtain this. Now, please note that because the body forces on the body, the body forces, they are specified, there will be no variation on this. Okay, so this is a rather subtle concept, but this is something which we are going to utilize uh, a few more times down the line. So please take note of it. So whenever something is actually given to us as part of the problem statement, uh, uh, and if you want to take the variation of that, that is 0. Because uh, as part of the proof, we do not know a priori what the value of the stress will be. That is, in that sense, we are seeking the variation of it and trying to arrive at the correct answer. So it is very much possible to consider the variations of the stresses, but it doesn't make any sense to carry out the variation of something which we know. Okay, because that is a nice a constant value given to us. So the first variation of this entire term, that is going to be 0. Okay, so the first variation of the stress equilibrium equation, from that we obtain this. The next thing, okay, so this is the first thing before the proof. The second thing that we want to uh, note is directly from the definition of the complementary energy, more specifically the complementary energy density. Okay, so this U dash naught, as we have seen in the earlier lecture, in the previous lecture actually, that was given by this in terms of the strain energy, U naught plus we had this sigma pq epsilon pq. You can write this as sigma ij epsilon ij, doesn't make any difference. So if we take the first variation of this, what we obtain is this thing plus this. So where we have just taken this part by part. Okay, and please note that we have already seen that this thing, this delta u naught, uh, that is nothing but minus sigma pq delta epsilon pq. So if you can refer to the previous notes to obtain this, to note this expression. Okay, so as you can see, this first term is going to cancel with this third term. So ultimately, what we have for the first variation of the complementary energy density is just this delta sigma pq epsilon pq. Okay, we could have written all of this in terms of ij, but doesn't make any difference. All right. So with this thing in our hand, we can now go on to the actual proof. So what we'll do is uh, we will because you see we have to ultimately prove that delta psi, this delta capital psi is equal to 0. We are going to start with this part, delta u dash. Okay, and if we can show that delta u dash is equal to the delta of this thing, then our job will be basically done, because then we can just transpose this thing to the left hand side and we can say that that entire thing is this psi, and then we can say that delta psi is equal to 0. This is our plan. Okay, we are going to we are going to try to show that delta u dash is equal to the delta of this thing. That's the plan. Okay, so let me go to the next slide. Delta u dash. Okay, we proceed step by step. This will be, so this is basically the u dash is the complementary energy, and we write that in terms of the complementary energy density. Okay, I have skipped a step here because I mean, you understand that this delta should have been outside, and then I take that inside. So I've skipped a step here, but you understand that. Okay, now just in the previous slide we have shown before launching into our proof two things, one of which was an expression for this delta u naught dash. You can just take a quick glance back here. So this delta u naught dash is delta sigma pq epsilon pq. So I'll write instead of this pq, I'll write this in terms of ij. Okay, so let me get back. So this is uh, epsilon ij. I write the epsilon first and then this variation term. Okay, this is exactly the same thing that we had written in the previous page. All right. Now, from our knowledge of the strain displacement relations, we can write this epsilon ij as half del ui del xj plus del uj del xi. All of you know this. We have done this so many times earlier in our course on applied elasticity. Now, very quickly, you note that this thing can be written as this plus half del uj del xi. So this is, first we have the u and then the j, and now here we have the j and the I. But what we are going to do here, when you multiply this thing with this, we are going to change the order of I and j in this sigma. Okay, that can be very well done because we all know that sigma ij is equal to sigma ji, at least for the typical cases that we are concerned with. There can be very special cases when that is not valid, but for this scenario, for our typical scenarios, that's perfectly okay. Now you see this term, if you were to replace the I by P and the J by K, and here in this term if you replace the J by P and the I by K, these two terms are exactly the same. Okay, they are perfectly the same thing, which means that overall I can write this as del ui del xj. So this is a little trick that we play here. All right, next what we'll do is a little algebra. Okay, we'll we'll use a little algebra to recast this uh, in this fashion. So what we wish to do is we wish to take both this ui and this sigma ji term, the delta sigma ij term, within the partial derivative. All right. Now, of course, you understand that by writing like this, we have effectively introduced another term like ui del del xj of delta sigma ij, which the term which was not present in the previous step. So that has to be subtracted out in order for this equality to hold. So we'll do exactly that. We subtract out the term which we have artificially introduced uh, while writing like this. All right. Now you note uh, we are in a very nice situation because in the previous slide when we were talking about those couple of things that we wanted to go into before launching into the proof, we have already shown that for the body to be in equilibrium, this term that is equal to 0. You can take a quick glance back here. We have already shown that del delta sigma ij del xj that is equal to 0. Okay, so we are going to use this thing. So maybe we call this as hash 1 and this as hash 2. So we have utilized uh, back here uh, we've already used hash 2 in this step, and in this step we are going to use the hash 1. Okay, so this thing is equal to 0 using hash 1. Okay, so we go to the we continue with this thing in the next slide. uh, so delta u dash, which is just the left hand side, that is going to be equal to this term. We write that again, del del xj ui delta sigma ij dv. Now you see what you're basically writing here. This is just the uh, so this is just the divergence kind of a situation here. Okay, so can we not write it in the next step? Sorry about that. My writing app kind of misbehaved here. Uh, as I was saying, this we can use it. We can use the Gauss divergence theorem here to convert this volume integral into a surface integral, because we note that this is like a this is the divergence basically. Okay, so this entity within the bracket, uh, here I is repeated, so this is basically just like a vector, and uh, that vector is represented by the single index j, and because we have this del del xj, so it is like the del del xj of some vj, where vj is the vector representing this entire thing, so that is like the divergence of the vector. Okay, so in the next step we can use the Gauss divergence theorem to convert this into a surface integral. And mind you that this is over the entire surface consisting of S1 and S2. Okay, uh, so this is going to be ui delta sigma ij nj. Okay, next what we are going to do is uh, we are going to uh, put this nj within the within this variational operator. And let me just write that and I'll explain why that is possible. Okay, so what we are basically using here is uh, we are appealing to the small deformation theory. Okay, please note that whatever we are doing here, it does not pertain to finite deformations. Finite deformations means the actual deformations, they will be non-negligible. So what we are basically saying is that even though we are considering the body to be deformable, but in reality the deformability is not so much that the geometry is changing significantly, so that if that were the case, then the unit outward normal to the surface would be varying, and then we would not have been able to treat this almost like a constant and take this within this variational operator. So basically what we are saying here is that we are using the fact that delta nj is equal to 0. Okay, so for all intents and purposes the geometry doesn't change. That is what we are using here. All right. Now what we are going to do is, you see this sigma ij nj, this is our very familiar form. We can write this as in terms of the fraction, okay, because you all know that sigma ij nj is nothing but ti. Okay. Using ti, fraction vector is equal to sigma ij nj. All right. Now it is time to consider the two parts of the surface separately. Remember that initially we had specified our boundary conditions, the traction boundary conditions over S1 and the displacement boundary conditions over S2. So we considered those two parts of the surface separately now. So first S1 ds plus S2 integration over the S2 part of the surface. The integrand remains the same for now. All right. Now you see what is happening. This first integration is over S1. But over S1, according to our statement, the tractions are actually specified. Okay, so this is a very, very important point to note again. So just like before, before we launched into the proof, we had said that because the body forces are specified to us, so the first variation of the body force is going to be 0. So also over the S1 part of the surface, because the tractions are actually given to us, so this traction is given to us over S1, so the first variation of the traction over S1 will be 0. Okay, so what we are left with is just this integration. So using the fact that since Pi is specified over S1, delta Ti is equal to 0 over S1. So we proceed. We have arrived at this form where on the right hand side we just have this integration over the S2 left. And please note that our original intention was to show that delta U dash is equal to, basically, so you can go back a couple of slides to the statement. You see, our original intention before launching into the proof was to show that delta U dash should be equal to delta of this entire thing. And you see this S2 is very nicely sitting here. So in terms of Sorry. Okay. Uh, my writing app again misbehaved. Sorry about that. Uh, so in terms of that, we are almost there. What we have to just do is one little step where we realize that now because we are considering the part of the surface S2, there it is the displacement boundary conditions which are specified to us. So the displacements are given to us, which means that again over that delta ui is equal to 0. Okay, so we can very well take this ui within this ti, this delta operator. Okay, so we can write it like this: using the fact that ui is specified over s2, so delta ui is equal to 0 over s2. Okay. And now of course we can take this delta operator outside the integration. There's nothing stopping us. And write like this, and therefore we can just transpose it to the left hand side like this, and then just one more step and take the delta out, and note that whatever is remaining within the bracket, that is nothing but the modified complementary energy. Okay, so hence proved. So this it seems, I mean, I'm sure that if you're a little bit mathematically inclined, the proof will give you a certain amount of satisfaction, but then it does leave us with the question that, okay, we have done a nice proof, so what? I mean, how exactly does this help us in solving problems? So by itself, this theorem involving the modified complementary energy, it certainly does not help us to solve any problem, but it does pave the way for the final theorem, uh, which will actually enable us to solve problems, okay, and which we are going to discuss in the next video. Thank you very much.